All right, so today I'm going to be talking about some of my work, challenging some of the assumptions that we have about what I consider to be the most profound beacons of the high redshift universe, Lyman alpha emitting galaxies. So I'll begin by giving an introduction about what Lyman alpha emitting galaxies, or LAEs, are and how we use them as a cosmological probe. Then I'll introduce you guys to the 100 square degree DECCAM imaging and narrowband survey, or ODIN. And I'll tell you a bit about how we select LAEs with ODIN, in addition to some early results that we have from a spectroscopic follow-up campaign with DESI. And the last chunk of my talk, which is probably about half of the actual talk, is looking at the star formation histories of Lyman alpha emitters to really truly test some of the assumptions that we make about them. And then I'll conclude. All right, so let's start with Lyman alpha emitting galaxies as a cosmological probe. So we typically think of LAEs as young, low-mass galaxies with low line-of-sight dust content and a lot of star formation. And because of this active star formation and the low dust content, we build up a lot of Lyman alpha emission that shines through very brightly in our spectra as this distinct emission line feature. And because of this feature, LAEs are relatively easily detectable from the ground, which makes them absolutely fantastic probes of distant galaxy populations. So when we have really large and reliable samples of LAEs, they become incredibly powerful tools for investigating the ancient universe statistically. There are a lot of things that we can do in this realm. We can trace out the distribution of dark matter in the universe, since LAEs tend to trace the large-scale structure. We can better constrain cosmological parameters, and we can study the star formation histories and physical properties of galaxies as they evolve through cosmic time. There are two primary methods that we use to select LAEs. The first is blind spectroscopy, where we use a spectrograph to obtain spectra over a wide field of view. This allows us to search for LAEs over a large range of different redshifts, and it's great because it provides direct access to our spectra, but it also means that it's incredibly expensive in terms of observations and computational time. So more traditionally, we use a narrowband imaging technique in which we combine broadband images that cover a wide range of wavelengths with narrowband images that cover very small ranges of wavelengths, and compare the brightness in those different images to infer the presence of our emission line feature. Because of the tailoring of those narrowband filters, we end up with LAE samples that are very specific in redshift. So this is great if you want to kind of look at timestamps of the universe. And the caveat here is that it requires spectroscopic follow-up to truly understand the sample purity, since we're essentially inferring the presence of an emission line rather than directly seeing it as we would with spectroscopy. So here are some examples of some of the state-of-the-art surveys that fall into each of these categories. I'm going to focus today on the 100 square degree DECCAM imaging and narrowband survey, or ODIN. Before I get into it, if anybody's interested in all of the nitty-gritty details about our survey design and science goals, you can feel free to scan this code from our 2023 paper. And if you decide after I start talking more that you are then interested, it will be in the top right corner. Great, so ODIN is a 2021 to 2024 NORLab survey program designed to discover LAEs through the narrowband imaging technique. We're accomplishing this using the dark energy camera, or DECCAM, which is on the Blanco 4-meter telescope at the Cerro Tololo Inter-American Observatory in Chile. Here's me about a year ago taking some observations for ODIN there. And for the dark energy camera, we built 3 custom-made narrowband filters with a really small full width half max of about 10 nanometers. And these filters are centered at these 3 wavelengths, which correspond to redshifts 2.4, 3.1, and 4.5. And these redshifts correspond to these time periods, which are equally spaced, and all exist during cosmic noon, where galaxies start to really form into complicated structures. And this is key for some of the other science goals we have for ODIN, like identifying protoclusters. Once we have that narrowband data, we pair it with archival broadband data from HSC, SSP, the Claude survey, and in the future, we're really excited to use LSST broadband data. And we basically designed ODIN to have several fields that overlap with LSST deep drilling fields. So in many ways, it's also kind of like a precursor survey to LSST, in which we'll be able to use all of our narrowband data and then apply it with the awesome deep LSST broadband imaging. And when all this is said and done, we expect to discover over 100,000 LAEs across 7 different fields of the sky, covering, as you might have guessed, roughly 100 square degrees. So I'm going to now transition into talking about ODIN's LAE selection techniques. And the results that I'll be showing will specifically be in the Cosmos field, which is the first field where we've completed all of our data. And again, if you're interested in all of the details, you can check out my 2024 paper here. So here are some of the filters that we use for ODIN. I have highlighted some postage stamp images from our narrowband filters, and this is for an LAE that has a redshift of 3.1, which we would see most prominently in the N501 narrowband filter, the one in the middle here. As I mentioned, we then pair this with the broadband data. So here is a composite image of broadband data, and then we can see different objects. So here is a comparison of what an LAE might look like compared to some other astronomical objects in our narrowband and broadband images. So LAEs are very dim and very compact. Now, this is one of the reasons why narrowband imaging is a great technique. Since they are so dim, especially in the continuum even, it's really hard to get all of the LAEs with just spectroscopy. So narrowband imaging is much better at this. We then have a non-LAE galaxy, a lower redshift interloper that's very bright and blue and a little bit less compact. And then star looks completely different. It's bright red. And from looking at these objects, it might be pretty intuitive discerning one from the other, but doing this manually obviously would be incredibly tedious. So we've created some sophisticated techniques to compare the brightness of each object in our different filters to infer the presence of that Lyman alpha emission line. So the way that we actually accomplish this is by using a technique that we call the hybrid double broadband continuum estimation technique. And basically what this means is we take 2 broadband filters that are nearby to the wavelength where we would expect to see Lyman alpha, and we either interpolate or extrapolate between those 2 filters to estimate what the continuum might look like at the location of the narrowband filter. That's where this hybrid double broadband continuum name comes from. This is a really useful technique because it allows us to utilize filters that don't necessarily have a contribution from the emission line feature. This allows us to select even dimmer LAEs And it also allows us to be really careful and intentional about the broadband filters that we decide to choose to maximize our area coverage and the quality of the photometry. So here I have some color magnitude plots to illustrate this technique. On the y-axis, we're looking at our narrowband excess, so comparing the double broadband magnitude to the narrowband magnitude. And the points here are colored by density on this specific plot. The gray points are a random subset of objects from our overall catalog. And you can see that they typically hover around a narrowband excess of 0, indicating that they have no emission line feature. And this shows us that our LAEs are distinctly a different population from the overall sample of objects. So we use these diagrams to select objects that have significant narrowband excess. We then eliminate any objects that are very bright in the narrowband, since these tend to be quasars. And we also eliminate any objects that have very large radii, because these tend to be low redshift interlopers. After that, we ensure that the emission in the broadband is at least as high as we would expect if our galaxy had a pure emission line. So if there was only an emission line, does that make sense with the amount of brightness that we see in the broadband that's getting contribution from the emission line? And this is a really key technique because it helps us to eliminate any spurious objects in the narrowband images. And lastly, we perform a sample purification. And we accomplish this by using a combination of both our narrowband data and broadband photometry. And this is specifically designed to eliminate O2 and O3 interloping galaxies, which have the largest emission line brightness compared to Lyman alpha, and tend to be the sneakiest objects to masquerade as LAEs in our narrowband data. Now, in the process of trying to eliminate these objects, we realized that we could actually do a pretty good job of identifying them as their own sample of galaxies to be studied. And I think the techniques that we use are really interesting. So I want to just take a couple of moments to talk about that. So here I have two GRZ color diagrams. The one on the left is looking at objects that have spectroscopic conformations. The right are objects that have photo-Zs. And we basically matched all of those objects to our initial source catalog, not just the LAEs. The subset of that catalog is in gray here, just bright sources. And in this dark gray kind of black are our original LAE candidates. The colored objects are objects that are in the particular redshift range that we might expect to find an interloping O2 emitter. And we've colored them by their narrowband excess. So we're coloring them essentially by their emission line strength if they have an emission line. And what we see when we do this is that the objects that fall into this redshift range with stronger presence of an emission line fall into a very compact and distinct region of GRZ color space, which you can see outlined in this yellow box here. And this helps us to identify any O2 emitters that might end up in our sample. Now you might notice there's this kind of glaring blob of objects in the green box farther left here that was known as the infamous blob for a very long time. And it turns out these are actually O3 emitting interlopers, so we use the same technique. You might notice that these objects are even brighter in the narrowband. They're yellower in color on this plot. And that is telling us that these objects are more likely contaminants in our higher redshift samples. So in order to really make sure that we are exclusively selecting these O2 emitters, what we decided to do is we first matched all of the objects in our LAE catalog to a spectroscopic redshift catalog, and we found that the objects that were indeed O2 and O3 emitters resided in those boxes where we had predicted they might. And when we took a look at those spectra, we realized that the objects, the O3 emitters, resembled what we call green pea galaxies. So for those who aren't familiar, green peas are a class of galaxies that was first discovered in the Sloan Digital Sky Survey Galaxy Zoo effort, which was a citizen science project. They are compact, extremely star-forming galaxies, and they're often thought of as low redshift LAE analogs, which is really interesting and kind of begs the question for why we would just throw them away. So in the future, I'm hoping to do a little bit more analysis with these galaxies, but for now, we've just identified them. And to just take one more precautionary step, I used a flexible stellar population synthesis model to create some synthetic spectra that looked like green peas and looked like an O2 emitter, and I plotted them in this same diagram as if we were to look at them through our filters, and they again resided in those boxes where we would expect them to. So this is all to say that green pea-like galaxies are the primary source of contamination in our high redshift samples. And the O2 emitters are a negligible source of contamination, but we are still careful to remove them. Once this process was all said and done, in the Cosmos field, we ended up with about 16,000 LAEs across our 3 redshifts. You can see from these spatial plots, which are colored roughly by density, that there are no profound systematic effects in our LAE sample as a function of spatial position. And you can also see that the regions of overdensity are unique in all 3 of these plots. These are not to be taken as any sort of analysis for protoclusters or filamentary structures, but if you're interested in looking at that, we've used these LAEs to identify protoclusters, and you can check out Vandana Ramakrishnan's 2023 paper as well as her 2024 A and B papers. And Danny Herrera, who's a grad student with me at Rutgers, is currently working on our clustering analysis. So there are lots of really awesome protoclusters that we can derive from these LAE samples. One of the other analyses that we decided to do with our sample is look at the equivalent width distribution. So we can think of the equivalent width as the emission line strength. And based on our classical understanding of radiative transfer in LAEs, we would expect that no LAEs should exceed an equivalent width of 240 angstroms. But as you can see in these plots, we do have some LAEs that exceed that threshold. We did a lot of analysis to try to understand how real these might be. Hopefully we'll do some spectroscopic follow-up on them. But what this is telling us is that it's very possible that LAEs have non-trivial radiative transfer scenarios or experience really complicated conditions in the interstellar medium. Now, that's a very inconclusive conclusion, but I want you to keep it in your back pocket as we move forward in this talk, and we can discuss a little bit more what that might mean. And lastly, we created some stacked SEDs of our samples. So SED stacking is a super helpful tool because it allows us to understand some of the global properties of our galaxy samples. And it's especially helpful for galaxies that have faint continuum emission, which is the case for LAEs. So here are our filter transmission curves with template spectra for each of our samples. And here are our scaled median stacked SEDs. They're all scaled to the I band, which is red. It's the second from the right. That's why it has no error, or the third from the right. That's why it has no error bar. And what we find is that these SEDs have key features that we would expect to see in LAEs. First of all, there's presence of the Lyman alpha forest decrement, which is characterized by the absorption of hydrogen gas clouds between us and the galaxy. We also see evidence of the Lyman limit, where we would expect to see complete absorption from hydrogen gas. So this shows us that our LAE SEDs are consistent with the expected features that we would hope to see in a sample of LAEs.
Nicole, one quick question.
Yeah.
Your guys' observing strategy was to go to a similar, like multiple of L star at these different redshifts, or was it like everything the same depth in terms of like AV magnitudes?
Everything was the same depth.
Okay, so
Yeah.
so you're probing brighter LAEs only at redshift 4.5.
Oh, I see what you mean. Yeah, so okay, so we did have different 5 sigma like limiting magnitudes for each of the samples. Yeah.
Okay.
Yeah.
But are you roughly probing like, I don't know, 0.5 L star, 0.1 L star to each one of these redshift ranges, or are they actually considerably different?
That's a good
UV
question.
luminosities?
Yeah, I'm not entirely positive. I think based on looking at the Lyman alpha luminosities, at least they seem pretty similar across the 3 samples.
Okay.
Yeah.
Okay. And the equivalent widths as well?
Yeah, the equivalent with distributions, I can
Okay.
go back to them for a second. One more. Okay. Yeah, so they are a bit different. They don't increase with increasing redshift. Which is what we maybe would have naively expected to see. So far what we're seeing is as we've added more and more fields, we'll start to get a better sense of how accurate this is. But the results seem to be fairly consistent in all of the fields.
Okay.
So, yeah. All right. Okay. So back to our SEDs. I'd like to compare for a sec our interloper populations to the high redshift LAE sample. So on the left here, we have our green P-like galaxies, and on the right are our redshift 4.5 LAEs. And what we see here is that our green Ps are way brighter. They have elevated flux density in the N501, R, N673, and Z bands, which correspond to the O2, H beta, O3, O3, and H alpha emission line features. And our green P SED doesn't seem to have a Lyman alpha forest decrement or the Lyman limit that we see in the LAE SED. So this has convinced us that these 2 populations are likely to have minimal contamination from one another, which is exactly what we would have wanted. And it allows us to use the green peas for further science rather than just taking them as a sample of galaxies that we'll throw away and might also have some LAEs within them. And we can show the same thing for our O2 emitters. They're brighter, they have elevated flux density in the N673 and Z bands, and they don't have those LAE features that we hoped they wouldn't. So again, we feel like these are most likely very different samples from one another with very minimal contamination. And before I move on, I just want to acknowledge that, again, all of this was for the Cosmos field, but ODIN's LAE samples are growing tremendously already. As we've introduced more and more fields, and these aren't even all of them just yet, even this week we have a couple more to add, but we already have a sample of 50,000 LAEs, which is the largest narrowband selected LAE sample to date. And as we've expanded this analysis to the other fields, Bailey Thompson, who's an undergrad at Rutgers, has been working with me and making a lot of strides in this effort. So we're really excited about all the additional science and additional number statistics that we'll have with ODIN. So I've been talking quite a lot about, the disjointness of our LAEs and these other interloping samples and trying to convince you that our sample is really robust. So I want to take a few moments to highlight some results from the ODIN DESI spectroscopic follow-up campaign, which has been led by Ethan Pinarski, who's a postbac at Purdue University. So in these plots here in the upper right corners, I have the postage stamp images that we looked at way back when, in the beginning of my talk. And then here we have some DESI spectra that correspond to each of those objects. And this process is not only important for understanding the purity and contamination of our LAE sample and improving our selection techniques, but it also enables these 3D statistical analyses that allow us to make sure we're properly identifying protoclusters, and we can do lots of other really interesting studies with LAEs as a function of 3D spatial position. And a lot of that is being carried out right now by Ashley Ortiz, who's an undergrad at Purdue University, and Vandana Ramakrishnan, who's a grad student at Purdue. So lots of exciting science happening with ODIN. Now on to our sample purity, which is work that I've been doing with Govind Ramgopal, who's an undergrad at Rutgers. So this is just for our Redshift 2.4 and 3.1 samples. We're still working on getting data for Redshift 4.5, but it's showing similar levels of sample purity preliminarily. We find that these LAE samples have upper limits in their purity of 95 and 97%, which is truly remarkable, especially for narrowband imaging. We're really happy with these results. But we wanted to understand the different sources of our contamination as a function of narrowband magnitude. So that's what we're looking at here. And each type of object in our sample is colored accordingly. So the blue are LAEs. And then we also have undetermined objects, AGN, that were at the correct redshift, but they're not LAEs. And then some contamination. And what we find is that most of our contamination come from objects that were just too dim to classify. So as I mentioned earlier, narrowband imaging tends to be much better at identifying dim objects than spectroscopy. So it's very possible that the vast majority of these undetermined objects are actually LAEs. We have a couple of low redshift interlopers as well, but these don't seem to be at any particular redshift in huge excess. So we're very happy about these results, and they're going to help us also to better constrain our Lyman alpha luminosity function, which we're just getting ready to submit a paper on by Gautam Nagaraj. So keep an eye out for that as well.
Did you try the spectral stacking at all? Like you said, assuming these are all at the same redshift as they've been selected.
Yes, so that is an effort that is underway by one of the undergrads at Purdue right now. And I don't know all of the results yet, but it's happening and will be published at some point. Yeah. They're really beautiful. I did look at them. Cool. All right. So hopefully at this point, I have convinced you that we have super awesome LAE samples and there's lots of great science that we can do with them. So I wanted to spend the rest of my talk talking about my most recent paper, looking at the star formation of LAEs in an attempt to challenge some of the conventional assumptions that we make about them. This paper is currently in review with AppJ Letters, but if you would like to take a look at the archive version, you can scan this QR code. So as I mentioned early on in my talk, we typically think of LAEs as young, low-mass galaxies that are experiencing active star formation. And conventionally, we think of LAEs as galaxies that are really experiencing their first burst of star formation. This originally comes from the notions of Partridge and Peebles' 1967, but it is a conclusion that we haven't really been able to fully prove or disprove up until this point. So this is mainly due to limitations in both data quality and analysis techniques. And now that we've made some improvements in both of those areas, we want to understand what the stellar mass assembly in LAEs actually looks like. And we want to understand if LAEs are in their first burst of star formation at the time in which we observe them. This may seem like somewhat of an existential question, but considering LAEs are often used for understanding galaxy formation and evolution, if we don't understand what precise stage of galaxy formation and evolution LAEs correspond to, it's hard to make definitive conclusions about that. And understanding the answers to these questions also help us to better understand the radiative transfer in LAEs. So the way that we get at answering this question is by going from SEDs to star formation histories. So SEDs are very powerful tools for uncovering the history of star formation and quenching throughout the entire lifetime of a galaxy from the beginning of the universe until the time in which you observe it. Here is an example of what an SED with lots of different data points might look like. And we can then fit a spectral template to this SED, and from there identify key features in the galaxy spectrum. For example, we can look at Lyman alpha to tell us about young stellar populations. We can age date the galaxy using Lyman alpha or with an age tracer. We can look at different emission line features to assess the ISM conditions. And as we move to the long wavelength end of the spectrum, we start to learn more about older stellar populations and any dust re-emission. So there's really a wealth of information here. In more detail, in order to accomplish this, we first fit our SEDs to spectral templates from flexible stellar population synthesis models. And these templates have well understood features associated with them. We then analyze that SED in tandem with additional features such as metallicity, IMF, dust attenuation, and absorption from the IGM. Basically all the things that take a generic stellar population and turn them into a galaxy. And then we use spectral features to infer the rate of star formation as a function of time, using tools like dense basis, which I'll tell you more about in a moment. And through these processes, we can uncover the physical nature of our galaxies, and as I like to say, better understand their life stories and their global properties. For our analysis, we match ODIN's LAEs in the cosmos field with data from CANDLES, the Cosmic Assembly Near Infrared Deep Extragalactic Legacy Survey. And I'll just point out very briefly that the version of CANDLES that you guys saw a few minutes ago is much larger than the area where there's CANDLES coverage, so we are shrinking our sample a little bit, but we still end up with about 70 different LAEs that become a part of this study. So then we perform our SED fitting, and in this process, we remove any narrowband or intermediate bands that contain Lyman alpha. Now, this may seem incredibly unintuitive based on everything I've been talking about, but I've alluded a couple times to the fact that we don't really understand Lyman alpha radiative transfer, so it would almost be misleading to include these filters in our analysis, so we remove them for now. And with that, we're still left with over 40 different filters. We then use the dense basis, non-parametric Gaussian processes-based star formation history reconstruction code. This is really where a lot of awesome advantages come into our study. And the reasons for that are, first of all, dense basis is non-parametric. This means that we can encode a maximum amount of information in a minimal and flexible number of parameters. It also means that we're not making any assumptions about the functional form of our star formation history. This is incredibly key because when you make assumptions about the functional form and you assume there's a burst of star formation and you're working with an LAE that you know is experiencing active star formation at the time of observation, that is always going to tell you that there is the first burst, the only burst of star formation at the time of observation, and it doesn't tell you about anything that happened before. So it doesn't help us to answer our question. This does. Dense basis is also Gaussian processes based, which allows us to reconstruct smooth star formation histories with higher resolution features, and we can also better constrain key parameters such as stellar mass. So here you can see the true star formation history for mock galaxies in blue, and in black you have the reconstructed dense basis star formation history, and they track really remarkably with each other and have similar areas where there are peaks of star formation. So back to LAEs, this is what we might expect an LAE, SED, and star formation history to look like. The star formation history, 0 is the time of observation, and as we move rightwards, we're going back in time to the beginning of the universe, so that's a look back time. And we can try to reconstruct this star formation history in our head for a moment. So on the left, we see that we have strong Lyman alpha emission. Here, the SED and the spectral template actually match each other fairly well for Lyman alpha. So we have active star formation at the time of observation, and we have kind of like a downward slope, which is telling us that there are virtually no older stellar populations. And that's exactly what we see on the right here. We're undergoing a maximum burst of star formation at the time of observation, not really much in the past. So this is what we would expect an LAE to look like based on that conventional model. It turns out,
Nicole, is this like Monte Carlo, or is it what are the different opacity lines? I also see the like interquartile range.
Yeah, so this is testing a whole bunch of different templates on the SED data points, and those templates help us to determine the confidence intervals on the right.
Okay, so do you modify the photometry like in each iteration and then refit, or how does it test it? Sorry, this is in the weeds.
That's a great question. I don't have a good answer at the moment, but I'm gonna get back to you on that. Yeah. Awesome. Okay. So we actually found that our star formation histories fall into 3 different archetypes. About 67% of them are in the first burst archetype, which is what we would have expected. And for that archetype, again, it's pretty self-explanatory. It's in its first burst of star formation at the time of observation. 28% of our LAEs are in a dominant burst phase. And what this means is that they have a past burst of star formation that was comparable in amplitude. The star formation rate was comparable in amplitude to what we see in our first burst LAEs. So that being said, there is still the largest burst of star formation around the time of observation. And then we found just a few, but a non-negligible amount of LAEs that fall into this non-dominant burst category, where they had their largest burst of star formation way prior to the time of observation. And if you look at the y-axis for the non-dominant burst, you might notice that it's a couple orders of magnitude higher than what we see for the first burst sample. And from that, you can see that even though there are these massive peaks of star formation in the past, the time of observation star formation rate is still incredibly high, which has something to do with why we detect Lyman alpha. So, in short, LAEs actually have several different stellar mass assembly scenarios. And if we take a moment to focus on the dominant burst and the non-dominant burst scenarios, the amplitude of past star formation suggests that a galaxy might have been an LAE at several points during its lifetime. This tells us that the LAE phenomenon could be both temporary and of varying duration, which is a really interesting and fascinating conclusion. And if we just focus on the non-dominant burst LAEs, we can see that they have much higher stellar mass than the other samples. And these LAEs look like they've built up over time, accumulating more and more stellar mass, which suggests that they are the product of galaxy mergers. So LAEs could be produced through galaxy mergers. We also wanted to understand the properties of our LAEs in the context of other star-forming galaxies. So to assess this, we looked at the percentage of stellar mass created at around the time of observation. So when I say that, I mean in the last 200 million years, which is roughly correspondent to the resolution that we have from the UV continuum. And we compare this percentage of stellar mass for LAEs to the same metric for a sample of Lyman break galaxies, which is essentially just a mass-matched control sample of non-LAE star-forming galaxies. The LAEs are in blue here, and then we have the control LBG sample in pink. And what we see is that the median percentage of stellar mass created in the last 200 million years is consistently higher in LAEs than in LBGs. And this is a statistically significant difference at redshifts 3.1 and 4.5. And a KS test reveals that these samples of galaxies come from different underlying populations. So neither the star formation histories that I showed nor this percentage of stellar mass imply that the overwhelming majority of LAEs are in their first burst of star formation at the time in which we observe them. What it does tell us is that most LAEs are experiencing what we call a formative burst of star formation. In other words, a burst that played a major role in the formation of the galaxy that we're observing. And in order to quantify the amount of LAEs that fall into this category, we combine the first burst and dominant burst archetypes, giving us about 95 galaxies that are 95% of the galaxies that are experiencing a formative burst. Before I finish off here, I wanted to share a small piece of the analysis that I'm doing now to try to see what we can understand about radiative transfer from these data sets. So I've just shown that LAE stellar mass assembly is much more complicated than we had naively thought. And we also saw that several LAEs have older stellar populations, which are often associated with dust. So in all these different scenarios of stellar mass assembly that produce LAEs, what are the radiative transfer mechanisms that are consistently making Lyman alpha easily detectable? So to begin to answer this question, what I've done is plotted the dust extinction as a function of the rest frame equivalent width, as a function of the emission line strength. Now, naively, we would expect that LAEs with higher dust extinction would have lower equivalent width measurements and vice versa. This assumes that Lyman alpha suffers from dust quenching due to the resonance scattering, which makes Lyman alpha photons essentially see like a multiplied dust column density. But that is not at all what we're seeing here. We're not seeing an inverse correlation. We're not even seeing no correlation. We're seeing a positive correlation. So if we instead assume that the photons that escape the LAEs didn't see a multiplied dust column, then this would imply that it's actually gas velocities that could be driving the radiative transfer of LAEs, and that would make more of a difference than the dust. These results could also be possible if we have a clumpy ISM, in which dust is clumped in specific regions, and the LAEs that we see, or the star-forming galaxies that we see, have a line of sight that doesn't align with those clumps of dust. So we get to see that Lyman alpha without it being completely absorbed. There's still a lot that I'm working on here to truly understand the radiative transfer, but this is just a start at it. So with all this information, we've created a revised model of what LAEs actually are as a population. So firstly, LAE stellar mass assembly is more complicated than we would naively think. Some LAEs have significant older stellar populations, and not all LAEs are in their first burst of star formation, but many are experiencing a formative burst of star formation. LAE may be a time-dependent classification where galaxies could potentially experience several different LAE phases or could have LAE progenitors. A small subsample of LAEs has undergone several massive bursts of star formation in the past, which shows us that LAEs could, in some cases, be the result of galaxy mergers where two different galaxies had their own star formation periods merged together, and that process incited star formation around the time of observation. And we also can see that LAE radiative transfer, or Lyman alpha radiative transfer, may be driven by gas velocities rather than resonant scattering, and might be impacted by a clumpy interstellar medium. So with all of that said, we arrive at my conclusions. Lyman alpha emitting galaxies, or LAEs, are classically thought of as young, low mass, low dust galaxies. And because of this, they are really profound cosmological beacons. ODIN is a state-of-the-art survey that's allowing us to discover over 100,000 LAEs, which enables us to map the large-scale structure, carry out protocluster analyses, measure galaxy bias, and do lots of other really fantastic and exciting research. We've developed some sophisticated techniques to select dim LAEs with remarkable sample purity, and it's also allowed us to set aside some other low redshift emission line galaxy samples whose star formation histories would be interesting to look at. The equivalent width distributions hint that LAEs might have non-trivial radiative transfer, and our classical model of LAE stellar mass assembly is incomplete, and our results from that analysis show more definitively that Lyman alpha radiative transfer is indeed quite complicated and probably driven by gas velocities or clumpy ISM conditions in some cases. So that's all I have for you today. Thank you so much for listening, and I'd be happy to take questions.
Question, anybody?
Yes. First disclaimer, I'm not a galactic person. So if this is very basic, feel free to move on to other more important questions.
I'm sure it will be an important question. Let's hear.
So I'm actually really interested in equivalent measurements. And when you say that the equivalent lists are much wider than model predicted, and when you say that the wind could be at play, or sorry, the gas velocity broadening could be at play, I was wondering, you possibly thought about different components of O2 or O3 emission that could be eligible from different parts of the galaxies.
Okay, that's a very interesting question. So when you talk about O2 and O3 emission, are you referring to the O2 and O3 equivalent widths, or how those might impact the Lyman alpha equivalent width?
I guess both of these.
Okay. Yeah, I can't speak too much on the O2 and O3 equivalent widths and how those might behave. Um, hmm. In terms of how that might impact the Lyman alpha equivalent width, um, we haven't really looked at the O2 and O3 equivalent widths. So I think what could be potentially informative, and this isn't something I've done yet, but maybe to answer your question in the future, um, what we could do is take some of our O2 or O3 emitters, since we have various equivalent widths associated with them, and look at their star formation histories and their SED fits, and see if we can pull out information about the dust there and other galaxy properties and kind of compare that way to see if they're similar to LAEs. Yeah, I have to think about it a lot more, but it's a very interesting question. Sorry, I don't have a more definitive answer.
Sorry that I asked something you.
No, that's fine.
Mark.
I will also ask a galactic astronomer ignorant question.
Ooh.
Not best. You talked about the possibility of like clumpy ISM. So can you say anything at all about the nature of the ISM you'd expect in these things? I'm thinking composition, size distribution, extinction curve, that kind of thing.
Yeah, I mean, we really don't have a good understanding. These objects are so far away that there's not that much that we can resolve about them. It's all kind of through inference. The interesting thing about Lyman alpha that has, or about LAEs that has caused me many an existential crisis is there are so many different components that impact the Lyman alpha that we actually see. Because what we see is not necessarily what's intrinsic, and it's probably not close to it at all. So you have to start to think about things like the opening angle of the Lyman alpha emission and how your orientation plays into it. So we're kind of working with these like fundamental aspects of what the galaxy looks like itself, but also how we're seeing the light escape through that galaxy and then travel to us. Yeah.
Okay, so at first order, you're basically thinking these are thinking of like large dust grains, and these are just basically taking light out of the line of sight.
Yeah,
Gotcha.
exactly. Yeah. Yeah.
Thank you.
Yeah.
Any other questions here on that? Any?
So how did you pick the narrowband filtered wavelengths?
Yeah, so this predates me personally, but speaking on behalf of ODIN, we firstly chose these filters during Cosmic Noon because we wanted to study galaxy clustering and to understand how the protoclusters that we see evolve into modern day clusters. So that was the motivation for the general wavelengths that we chose, but they were also strategic with some anticipation of the low redshift interlopers that we might expect. So I'm going to go back to a previous slide for just a moment here. Once I find it, maybe somewhere around here. Okay, so here you can see one of our green pea spectra. And basically at our lowest redshift with the N419 filter, we expect to have some random like spurious object type of contamination. As we move to redshifts 3.1 and 4.5, low redshift galaxy interlopers become the biggest problem in selecting really pure LAE samples. And that can mess up all sorts of different things with clustering analyses and halo occupation, distribution, and all of that. So if you look closely here, in the N673 filter, we end up with either one or two O3 emission lines when we have a green P. And in our N501 filter, we end up with O2. And by setting up the filters in such a way, it allows us to have a cross check for what we would expect to see in N501 when we think we might have an interloper in our high redshift sample. So the part that I kind of left out, as to not bore you with all the details about how we remove these objects, is that in addition to looking at the narrowband excess in the filter where we have the O3 emission line, we also look at the excess in the N501 filter where we expect to have O2. So it was strategic in that way. The last piece of why we chose these filters is because they correspond to equally spaced periods in the universe's history in terms of time. So it allows us to kind of get these like time stamps.
So you talked about fitting SEDs. How many data points do you need to fit an SED?
Successfully.
Well,
I have a feeling the answer to that question will change based on who you ask, but we do implement a chi-squared cut to make sure that we're happy with our SEDs and we feel like they're doing a good job of fitting our data. So I think the most important thing is making sure the photometry is also really robust. So we do exclude like IRAC bands 3 and 4, which don't have as robust photometry. So yeah, those are the things that we care about
So
more.
The motivation is you mentioned that when you were trying to find the Lyman alpha emitters, you were sort of taking the two broadband filters and estimating what do we expect the narrowband brightness to be. But I think you actually have 5 or 6 broadband filters plus your 3 narrowband filters, which is that enough to then just take this raw photometry in all of your broadband and all of your narrowband and fit SEDs and say, and use that as a detection method?
Yeah, this is something we've thought about a bit. It's obviously more computationally intensive, but it's definitely doable and it's definitely an option. So it's not something we've tried yet. One sort of related idea that we've been thinking about is trying to use a convolutional neural network on the images, which is, same sort of idea, but a different technique where you're looking at all of the photometry there, just a composite, and trying to do our LAE selection that way. But that has some issues when we're looking at dim objects. If you've ever looked at images of LAEs, they're like smudges. But yeah, essentially what you'd be doing there is fitting a power law to many more data points instead of just 2. But typically the way that people do narrowband imaging is they just use 1 broadband filter. So even by using 2, we're much more robust. And because these selection techniques seem to work really well, then you could argue what's the point of doing something that's more computationally expensive if you can get away with a really good selection with just 2 filters.
Yeah, Annie, please.
I feel like as the radio person, maybe I missed it in the first part of your talk, but what fields is ODIN covering? It's Cosmos and
Yeah, Cosmos, Sheila, which is a HETDEX field, so we have comparable spectroscopy there. EDFS, Deep 2-3, CDFS, they're the 2 CDFS fields, I believe, and that gets us to 7.
okay.
XML,
And XMM LSS, that's it, I missed one.
all the famous ones that have
All
all the radio data.
So there's quite a lot of radio. Have you
Yeah.
looked at
And
it?
also X-ray.
Yeah, I haven't looked personally yet. Yeah.
I'll take another tack, which is so like leveraging off of Andy's question. I mean, AV from SED fitting, even with the wonderful data in Cosmos, not entirely trustable, I would say. And so, but there is like super deblended catalogs for mid-infrared data or far infrared data in Cosmos, and one could think about stacking, the dominant burst LAEs or the non-dominant burst LAEs, and seeing if you get a signal out of that to see if that comports with the amount of dust content that you would expect from your fits there.
That's
Have you tried that?
not yet.
Okay.
Yeah.
So is that AV you get in the galaxy, or is that between the galaxy and the?
It's internal extinction.
How do you distinguish between internal extinction and field and line of sight extinction?
Your Milky Way, correct, your dog shape. All that's left is the galaxy.
Yeah, so all the photometry I've shown here is Milky Way dust extinction corrected.
And then there's an IDM correction as well, but that's only in one band. Any other questions here or online? Yeah, please.
Do you have any plan to see the spectroscopic follow data? I think you already mentioned DESI, but to better understand the radio transfer of Lyman alpha, it's really obvious to see the Lyman alpha profile directly.
Yeah, so I haven't done that with these galaxies yet. I'm gonna put in a spectroscopic follow-up proposal. But there's some really interesting work that has been done with Muse. Yeah, looking at Lyman alpha emission line profiles. So I think it would be really interesting to try to use a technique like that and look at our different the star formation history archetypes and see if there are any relationships there. Yeah, but right now, like with the DESI spectroscopy that we have, you can sometimes see if it's a double peaked Lyman alpha emission line, but that is about it. Yeah.
Okay, any further questions? If not, let's thank Nicole again.